All right. Well, welcome to Chapter 5, Data Organization and Descriptive Statistics. This is going to give you a lot of basic information and terminology. For descriptive statistics, let's go ahead, jump right in. Looking at organizing data and descriptive statistics. Data can be organized in a frequency distribution, a table in which all of the scores are listed along with the frequency with which each occurs, or a class interval frequency distribution, a table in which the scores are grouped into intervals and listed along with the frequency of score in each interval. Qualitative variable is a categorical variable with each value represents a discrete category, and we'll see that here in a second. Quantitative variable, a variable for which the scores represent a change in quantity. Okay, so looking at this, you can see that down here you have names, so Republicans, Democrats, Independents, uh, the yeah, Socialists, and the Communist. And so those would be the qualitative uh, aspect, right? The qualitative variable, because it's a name. Think quality, qualitative. This is also the nominated or the nominative uh, variable too, right? Because it's the name of something. It's the lowest level of variable that we can have. Along the side here is the frequency distribution. So for this category, there are 11 Republicans, there are 12 Democrats, there are 4 independents, there are 2 socialists, and there's one communist for the distribution of the 30 individuals. Okay. In this graph, we have an IQ score, right? So that is a ratio variable, right? Because there's a 0 over here someplace, and then there are these scores. And so this is called a histogram, and there are 30 individuals on this in this data set. So as you can see, um, there are each of these dashes is a number here. And so there's one for 83, one for 86, one for 89, one for 92, nothing in 95, 98, 101, nothing in 104, nothing in 107, nothing in 110, 113 is 2. Sorry, I haven't been reading those off. 116 is 3. 119 is, uh, sorry, 2. 122 is 0. 125 is 1. 131 is 1, and 134 is 1. So we're going to learn about the curve here and the distribution and what that looks like too. We'll have names for that information coming up. So, and you can see, right, 83, 86, so they're skipping every 3. So they've actually blocked together these individuals here. They could be 91, 92, or 93. These individuals here could be 97, 98, or 99. So these have been also interval blocked together. So to go back to see the class interval frequency distribution, a table in which the scores are grouped into intervals and listed along with the frequency of scores in each interval. So hopefully this is a good example for that for you. And you can see that the score, even though it says 83, is actually an interval because all of these intervals are exactly 3 apart. So the score is actually could be 82, 83, or 84. This one could be 85, 86, or 87. This could be 87, 88, 89 or 90, and so on and so forth. So these are grouped by intervals, not necessarily by the actual scores. Then we have a frequency polygon of IQ score data for 30 individuals. And again, we can see 83, 86, and this is, again, a frequency interval, basically, because of the same thing. And you can actually look it up as it goes up and down there. Descriptive statistics. These are the numerical measures that describe a distribution by providing information on the central tendency of the distribution. We'll talk more about that. The width of the distribution and the shape of the distribution. Each one of these has particular terms that we use. Measure of central tendency, a number that characterizes the middleness of an entire distribution. So hopefully you've heard these names before, but there's mean, median, and mode. Mean is the arithmetic average. We can use that with intervals and ratio data, not for use with distributions with few extreme scores. Okay, the few extreme scores are called outliers, so we have to account for outliers in our data. One outlier could really skew the way that the data look. Okay, so the median is the middle score in a distribution, the actual middle score. If you had 15 scores, then it would be the one that is at number 8. If you put them in order from the lowest to the highest, you would pick the middle score. You can do that with ordinal, interval, and ratio data. The mode is a score occurring with the greatest frequency. So just out of the highest level, it's whichever one is the highest. So if we looked at our chart here, here's the highest. It occurred 5 times, and that would be 107. So just to give you a little glimpse of that. And you can use nominal, ordinal, interval, or ratio data. This is not a reliable measure of central tendency, and you can see why. You might have 5 of something in the beginning and then have 4 of everything else, but so it wouldn't really show you the truth as to the central tendency. The measure of variation is a number that indicates the degree to which scores are either clustered or spread out in a distribution. The range is basically the difference between the lowest and the highest scores in a distribution. And we'll see more of these as we go along. The average difference between the scores in the distribution and the mean or central point of the distribution, or the square root of the average squared deviation from the mean. Sounds like a bunch of jargon. We're going to explain it here in a second. The average deviation is like the standard deviation, indicates the average difference between the scores in a distribution and the mean of the distribution. Here is the raw score formula. So this is sigma, which just means the sum of x squared minus the sum of x squared divided by the total number of participants, n, right? So you've got the sum of x squared, so you're going to square all the x's. Then it's minus the sum of x and then square, and then you're going to divide by n, and then all of that divided by n, and you will take the square root of all of that. So if the sum of all the squares is 169,860 minus the sum of x squared, so 2,220 is x, the sum of x, I should say, and you're going to square that, and then that's divided by 30. The whole thing right there is divided by 30, and then you take the square root of that whole thing. So then we get 169,860 minus 4.9 million divided by 30. Over here, 4.9 million divided by 30 equals 164, 280. divided 169 minus 860 minus 164, 280 divided by 30. The subtraction there is 5,580 divided by 30 equals 186. Divided by, our square root of that is 13.64. So that is the standard deviation raw score formula. Okay, so types of variation measures are the range, the lowest to the highest point, primarily with interval and ratio data, a simple measure that does not use all the scores in the distribution in its calculation. The average deviation is the average distance of the scores from the mean of the distribution. So primarily interval and ratio data, a more sophisticated measure in which all scores are used, but which may not weight extreme scores adequately. And then standard deviation, the square root of the average squared deviation from the mean of a distribution, primarily interval and ratio data, and the most sophisticated and most frequently used measure of variation. Okay. And again, measure of variation is important because we want to know how well any point is represented by the data that we see. Now, when we do this, we can see when we put data on a graph like we did before, we have a normal curve, which is a symmetrical bell-shaped frequency polygon representing a normal distribution. Normal distribution is a theoretical frequency distribution that has certain special characteristics. So a true normal distribution is, we'll see it here in a second. The kurtosis is how flat or how peaked a normal distribution is. So as we can see, here's a normal distribution. This side is symmetrical to this side. So the scores are going to gradually go from nothing up to the mean, mode, and median. Now, if you notice, they're all same, mean, mode, and median in a normal distribution. This theoretical construct is by which we go by to see if things are within a certain probability of happening, okay? And then we have our downslide over here towards the positive end. So this is the negative end, this is the positive end. In the normal distribution, the mean, mode, and median all happen at the same place. Mesocurtic, normal curves that have peaks of medium height and distributions that are moderate in breadth. Leptocurtic, normal curves that are tall and thin with only a few scores in the middle of the distribution having a high frequency. Plateocurtic, normal curves that are short and more dispersed, so broader, and we've got pictures of each of these here. So the normal curve is the mesocurtic, fairly consistent, goes up and down. The leptocurtic, you can see, has a few or most of the scores here in the middle with few on the outside, so it kind of goes up and then down. And then plateocurtic, the scores are more evenly distributed, so the curve itself is relatively the same height as you go across. Okay. Now, when you see a positively skewed distribution, these names kind of seem to not go well, or doesn't seem to make sense, because you would think that positive would be on this side. But remember, this is this side here is where it's up, and then the skew goes down. His slope goes down that way. So the slope, the long slope, goes down to the positive side. So it's positively skewed because you have very few numbers here, and then you have a big increase, and then it goes down. The positively skewed distributions, you'll have the mode here because it's the highest number. You'll have the median in between the mode and the mean, and then the mean will be over here. And this accounts for some higher scores on this end, the positive end. High scores, positive end, positively skewed. Okay. On this side, you see that there is a lack of high scores over on the positive end, but they're distributed over here on the negative end. Gives you the reason why it's negatively skewed. Okay, so in this, you'll notice that the mode again is at the highest point because that's what the mode is. The number that happens the most is the median, and that's where that is. And then the mean is over here. So you notice that the mean is on the long side of the tail, and the mean is on the long side of the tail. And so that is how a positively and negatively skewed distribution looks like. We can use our statistics to get the z-score, which is a standard score, a number that indicates how many standard deviation units a raw score is from the mean of a distribution. Formulas for a z-score transformation are z equals x minus the mean of x over the standard deviation, and or the standard score. Z equals x minus mu over the population. So x minus the mean for the sample over the population. If we look in our books, so on page 117 in your book, the average deviation is essentially the average distance of all the scores from the mean. And if we look at table 5.8, which is on the next page, I think, we can see that the average mu is x minus mu. That is basically what a standard deviation table looks like. And these are how we actually end up with getting our ANOVAs in the future here. So that's why learning this is going to be important. If you notice that the mu here is 74, that's the mean for our sample. We have 74 on your book. If you look at this is your column. You have 74. These numbers here are your actual score. So you have 45 minus 74 is minus 29. 67 minus 74 is minus 27. 56 minus 20 or 74 is 20. And you just keep going down for each one of those scores. And that is your x minus mu there. Okay. And then you're going to divide that by the population, or in this case, n. So your omega, this score right here, if you look on page 119, that is equal to the standard deviation, or to the sum, the square root of the sum of x minus the mean squared, okay, divided by the number of n. And that gives you the 13.64. Okay. So it's important to know how to get these things right. So S is your sample standard deviation. And on page 121 of your book, Z equals X minus the mean of X all over S. This is the same as saying Z equals X minus mu divided by the omega. Okay? So both of those numbers we're able to get from plugging in these numbers down here. All right. If you notice in your chart on page 5, table 5.9, on page 120, we get X, right? X minus the mean, the mu, and then X minus mu squared. So minus 29 squared is 841. You'll notice that all of the numbers there are positive numbers, so they're not canceling each other out. That's how you get the sum of X minus mu squared, 5,580. And with that number, you're able to do the data with the formulas, and that is the variance. So again, briefly to look at this transformation of the z-score, the z is going to be the individual score minus the average score for whatever test that you're looking at, and you're going to divide it then by the standard deviation. And so that will tell you how far the individual is from the mean score of the whole exam. It only gives you a standard score. So the score that you get would be in standard deviations. You look at the text, it gives you some other examples on page 128. So we'll just start there in the middle of the page. Suppose you administer a test to a large sample of people and computed the mean and the standard deviation of the raw scores with the following results. So the mean is 45 and the standard deviation is 4. There are 4 individuals who took the test and had the following scores. So you have Rich, Debbie, Pam, and Henry. The scores are as follows: 49, 45, 41, and 39. And so as you go through, the X score for Rich was 49. 49 minus 45 equals 4. 4 divided by 4 equals 1. So Rich is positive on the positive side of the scores, 1 standard deviation. Okay. Debbie, on the other hand, was at 45. Hers z-score is 0, which means she scored exactly the mean of the exam. There's no standard deviations to either side. Likewise, we could take Henry. So Henry was 39. So 39 minus 45 is minus 6. Minus 6 divided by 4 is 1.5 to the negative standard deviations. So Henry scored 1.5 standard deviations to the negative. Okay. So the z-score, the standard score, indicates how many standard deviation units you are from the raw score. The raw score is from the mean. Formulations are as follows, and we already went over them. Tomorrow, when we're in class, we can try to or when we're on the Zoom link, try to uh, go over these and answer some questions on how to do these things. So we'll get it so that we can do that. The standard normal distribution, a normal distribution with a mean of 0 and a standard deviation of 1. Probability, the expected relative frequency of a particular outcome. So if something happens within one standard deviation, there's a 64.26% chance that it's going to happen within one standard deviation. 34.13 plus 34.13. Within two standard deviations, we're going to add on to the 64.26, 13.59, doubled again, so another 26, and 26, 27.18 plus 64.26, so 27.18 and 64.26. And with that new one, we get 91.4% or 44% of all of the possible solutions or tests would fall into this category. So within two standard deviations of the mean, both ways, -2 to 2, +2, we are looking at 91.44. The third standard deviation away adds another 4.3 to it. So 2.15 doubled, right? And hence we've gotten 95.74%. And then the rest is the 0.13. That doesn't sound right. So let's go 34.13 is 64, or sorry, 68. There we go. That seems a little bit better. So sorry about that. 68.26. Then it's 90 or 20 plus the 27 is now 95. 0.44 plus the 4.3 is now 99.74%. There we go. With the remainder of the tail, the 3 to the rest of the standard deviations away from it is 0.13 for the rest of the tail, or 0.26. So you can see that's the area underneath the curve for standard deviations. And remember, the standard deviations are basically the z-score. So one standard deviation is 1z, 2z, 3z, -1z, -2z, -3z. When we look at the percentages and try to calculate some other things, those are going to be important. So with one standard here, 5.8, that's the z-score is 1. One standard normal curve, z-score of 1. Figure 5.9, standard normal curve with z-scores of -1.0 and -1.5. So over here. The percentile rank is a score that indicates the percentage of people who scored at or below a given raw score. So important to remember, at or below, okay? We will do some calculating tomorrow during the live portion of the class for those of you who want to do it. If you think that you've got it and you think you can understand it from the book, then that's fine. We can practice it in your leisure time. I'm sure you can look it up. There are some chapter exercises that are available to you on page 138, and you can put those tomorrow. We'll try to put those in and get the information that we're looking for out of it. Okay, and so should be interesting to do some of this. I'll get it set up so that we can go over it in, and we'll use sorry, we'll use Excel to do that. All right. The description of normal asymmetrical bell-shaped unimodal curve. Z-score transformation is possible, yes. Percentile ranks and proportions under, yes. Normal curve. Positively skewed, you can still do Z-score application transformations, but you cannot do the percentile ranks because of the skew. The negative one, again, you can do positive, you can do Z-score transformations, but you can't do the percentile ranks and proportions. For that, you need the normal curve. And for exercises, always assume that we're doing a normal curve, unless otherwise said. So just in summary, we're looking at the measures of central tendency, mean, median, and mode. Remember, the mean is the average. The median is the one that's actually in the middle. If you have two numbers that are in the middle, so if you have 18 scores, then it will be the score that is 9 and 10. And if they are different scores, then it will be the average of those two scores would be your median. Okay. And then the mode is the score that just happens the most. If you have multiple scores that happen the most, and they actually are the ones that happen the most. So if you have a score of 5 and two scores of 6, then 6 happens the most, and it is also the mode. If you have one score of 5 and you have two scores of 4, then you have to go with the 5, even though there's the scores of the 4 in different categories might be more altogether, they're less than the 5. The distribution may be normal, positively skewed, or negatively skewed. And just remember, whichever way the tail goes is the way that it's skewed. So the tail goes to the right, it is positively skewed. If the tail goes to the left, it's negatively skewed. And calculation of the z-score transformations as means of standardizing raw scores. And so tomorrow we'll go over that as well. And if nobody shows up for the online part, then what we'll do is I will just make another video and I'll go over how to do those separately. Okay? I hope you all are doing well and have a good day. Bye-bye.